So what is robustness? Let's go back to deep learning, the concept of deep learning in general. Our data was our source code. Then we designed models, either hand engineered our models or automatically found them. We tried to make them more efficient by taking into consideration the computational capacity of our devices. We trained our model using mostly a stochastic gradient descent. That was our compiler. Now we end up with a software that you can put it in your drone, you can put it in your self-driving cars, you can put it in your smart devices, or you can put it in your robots, or you can put it on your homepage to do something interesting. As soon as an image comes in, you're going to do something interesting with it. So now you're taking the resulting algorithm that's coming out of deep learning, and you want to put it into production. And whenever you take something to production, bad things could happen. There could be attacks on that algorithm. There could be viruses. There could be adversarial attacks on your device. And you want your target application to be as robust as possible. And that's why we're going to cover robustness, because it's very important. In the end, the objective of deep learning is to give us an algorithm that we're going to use it in production. And we don't want the algorithm to fail for random reasons. It could be targeted attacks or even untargeted attacks or even random events. So let's start with the first paper that started it all and try to study robustness and how things are going to work. So many people confuse generative adversarial neural networks with adversarial attacks. These are two separate topics. They have the similar names, adversarial, but the aim is totally different. In one of them, the aim is to generate and come up with generative models, generate images for creative work, for instance, and for learning the underlying distribution. Adversarial neural networks or adversarial attacks are about robustness of our networks. So these are two separate topics with similar names. Okay, let's get started. Let's say you have an input image, X, it's m-dimensional. So we are concatenating or flattening an image, and it's going to give you m for the total number of pixels. So that's your input image. And we are going to take a look at the activation value of some particular layer inside our network. So that's going to be a function, that's going to be a function of X, and the values are going to be n-dimensional. We can take a look at the units of phi and try to see what the network learned. What is the network learning? What features is it coming up with? So remember, we are not doing feature engineering by hand anymore. We are letting the network to find the feature for us. And now let's say you want to interpret those features. And people were trying to do that. And how would they, one way of interpreting that or coming up with an interpretation, this phi is n-dimensional. You can take a look at one of the dimensions. So you can take a slice. And that's basically the inner product with a unit vector in your coordinate system. And that's going to pick out a single value. So this is going to be one-dimensional. And it's going to pick out only one of these dimensions, one out of the n dimension of your feature. And let's try to study that. Now that you have a single value, you can optimize it. You can say, I want to find the argmax over some images that I haven't trained on before. And as soon as you find it, it's gonna give you the image that's gonna activate that particular feature the most. So there is a question from Theodore. Are we maximizing over all X and all EI? No. You pick an EI, you choose it. You are interested in the 10th feature, for instance. You choose E10. Now you maximize over X. So I'm being careful here. It's argmax over X only. And that's a great question. So this one is fixed. You pick it, you fix it. You want to see what image in your data set is gonna activate this particular neuron the most. So it's gonna give you a way to visualize what type of images this particular neuron is sensitive to. And as I said, EI is just a natural basis vector. It's a vector that's 1 and then 0 everywhere else. And it's 1 at the ith location. So we are only picking out one of these n dimensions. So we are picking out that hidden unit, the ith hidden unit. And what is I? Where are we searching over our images? We are searching it in a held out set of images that we haven't trained on. So we haven't trained the network on this set of images. So I is not part of our training data. And people started interpreting that. They said, okay, this unit seems to be sensitive to lower round strokes. For instance, this one, this one, this one. So these are lower round strokes. So now we are interpreting that particular unit. This other unit seems to be sensitive to upper round strokes. So there is a round stroke on top. Or it could be lower straight strokes. This unit is sensitive to left upper round stroke. So it's left upper round stroke. Sensitive to diagonal straight line. But there is nothing intriguing about this. But what is intriguing, and hence the name of this paper, is that there is nothing special about EI. And that's exactly going back to Theodore's question. And that's why I say it's a great question. So there is nothing special about EI. You can change EI to any random vector in Rn. So any random vector, you can do the same exercise, and then you can start interpreting. You can say all of these images are sensitive to upper straight strokes or a lower round stroke. You can do the same interpretation for it's a direction sensitive to lower left loop. So there is a loop here. Direction sensitive to round top stroke. Direction sensitive to right upper round stroke. So you can start interpreting them. Similarly, not only you see it for the numbers and digits, you're gonna see it for images. If you pick EI, you can say that this unit is sensitive to round spiky flowers. These are round and spiky flowers. You can say, whenever I say direction, there is a random direction. And whenever I say unit, that's just one of these EIs. You can interpret a random direction in a similar fashion. For instance, this image or this set of images are sensitive to spread shapes. So it's a flower, that one is spread. I think that's a fan. This is a wheel, flower, etc.
So do they pick just random vectors and find these images which maximize this inner product and then stare at what they get and then try to interpret the meaning of the vector V? Or is there something systematic that they're looking for or like a priori feeding into this?
No, that's exactly what I've been doing. You pick EI, one of your units, you maximize that over a set of images, and then you report those images.
You look at the images and say they all share this property. And so these properties that you're writing out are more of like a human-based interpretation of the commonality.
Exactly.
Okay.
That's correct. And they make sense.
Way of doing it the other way around?
The other way around is when you are doing hand engineering. You hand engineer some features. For instance, this could be one of your features. You can, in your images, you can look for direction sensitive to upper right, upper straight stroke. And that could be a column in your data set.
Got it.
And once you have your data set in a tabular format, a classical machine learning technique can do it.
Got it. Okay.
Yeah, but now you have some features, you want to interpret them.
Yeah, cool.
And this is what people were doing with the features, with that particular hidden unit. But then this paper came along and said, there is nothing special about that unit. Actually, any random direction, you can start interpreting that.
This is actually a question I've had like throughout this class is is there a way of looking at like these digit classifiers that output a number or a softmax with a probability of the different digits? Is there a way of feeding the network backwards? So passing in like digit 10 and seeing what image the network generates, or then this kind of seems like a not exactly that, but like a kind of a proxy of doing that, like figuring out which images in this case activate a certain neuron. Is there a way of looking at which images activate or like what back propagating from a digit 10 or a digit 9 or a digit 8 would generate as an input image?
Yes, so we are going to go through that when we study some papers that try to analyze what the network is doing.
Okay.
Maybe visualize it, where the network is focusing on, etc. And we are going to see that.
Cool.
And one approach is what we are doing here. It's you pick a neuron. What type of images activate that neuron the most?
Got
And
it.
this is sort of going backward.
Hmm.
But yes, we are going to see all of that later on.
Thank you.
But now this is an intriguing property. And the interpretation is that no specific direction has any particular meaning. It's actually the space spanned by this function that is having a meaning. So it's the entire space or the entire manifold that you're finding. And all of them all together, they have a meaning. Yes, you're finding some features, but each single one of them may or may not be meaningful, but it's the entire space. There is another intriguing property. Any questions so far? Because I'm changing the topic slightly. Okay, perfect. Now let's look at the networks, and these networks seem to have some blind spots. Let's take a classifier. You take an image and then you classify it among one of these k options. You classify it as a number 1 or as a number 10, or image number 1 or image number 1000 in the case of ImageNet. So you have a classifier, and we are looking for blind spots. What is that? We are going to take x, our input, perturb it a little bit with another vector r, push it through our neural network, and we want to classify it as label L. And I'm going to tell you what is L. And we want this perturbation to be as small as possible. So the objective is to find an image, x plus r, that is as close as possible to x and classified wrong by the network. So it means that if you can solve that problem, these are counterexamples to what the classifier is supposed to do. So if an image is perturbed slightly, the network should still predict the same outcome. And basically, we shouldn't be able to solve this problem. These are small perturbations.
What's the rationale behind that bottom condition? Is that saying that x plus r needs to be binary or just some number between 0 and 1?
X plus r, what does this mean? That's a great question. What does this mean? It means that you still have to be an image.
So that's the interval 0 to 1 or that's not the set 0, 1.
No, it's interval 0 to 1 because these images x
are normalized.
Yeah. From 0 to 1.
Got it.
Now you want whatever that you're adding not to escape your domain.
Thank you.
You don't want it to be from 0 to 1 point. One of the pixels have a value bigger than 1 or smaller than 0. And the other objective is you want it to be minimized. You want to be as a smaller perturbation as possible. And why L should be not equal to f of x? The reason is that, let's go backwards. If it is equal, what's going to happen? Then r equals 0 is a trivial solution. So that one has a trivial solution, and we don't want trivial solution. And we want our network to actually make mistakes. So you pick L. Let's say you want number 2 to be classified as number 6. So you pick 6, that's going to be your L. Your network is currently and correctly giving you a 2, but now you want to confuse the network. You want to attack it. It turns out that solving that problem is not easy. This is high dimensional, and enforcing this constraint is not easy. You can enforce it through a loss function. So you introduce your loss function, and your loss function takes as input an image, gets the image, push it through the neural network F. It's going to give you the prediction of the neural network. You're going to know the ground truth, and your loss is going to give you a number that you can optimize over. And rather than solving that problem, we're trying to solve this problem. We still want to minimize the norm of R, and we want the prediction of the network to be as close as possible to the label that we wanted. And this one is just not that big of a deal because you can cut it. If it escapes your domain, you can cut it to the boundary. So that's going to be your objective function. The second part is trying to enforce this part. But now things are differentiable, and you can take derivatives and try to optimize that. And the optimization that we are going to use is going to be box constraint LBFGS. It's just LBFGS, and it's box constraint. And it's box constraint because you want it to be within the box. Once you use that, you will come up with your perturbation. So a small perturbation can make your network confused. So these two images are indistinguishable. The perturbation is very small, but the network is going to get confused. It's going to give you another prediction. Similar thing here. A similar thing here. So to human eye, it's very easy. We know that it's the same dog, or that's the same car, school bus. This is intriguing. And something even more intriguing, it's not for this particular network and for this particular structure of the network. These adversarial examples actually mess up with the predictions of totally different neural network structures. For instance, you can design your adversarial examples for a fully connected neural network with 10 layers, and it's going to make 100 mistakes, 100% mistakes. You take the same examples, you feed it a fully connected with 10 layer, you feed it with another, you feed it into another network structure, and you're still confusing the network. So these adversarial examples, that's why this problem is huge and very intriguing, is that they are universal. You design them for a particular network and for a particular data set, but they're gonna mess up with the predictions of another type of network trained on another type of data set. So the conclusion is that adversarial examples are hard even for models trained with different hyperparameters. I think we are 1 minute over time. For those of you who want to stay and ask questions, I'll be around. And for those of you who want to leave, you are more than welcome to.
If you add these adversarial examples to the training data, do you end up with a new set of adversarial examples that still generalize?
Say it again.
So you come up with a set of adversarial examples, right? You come up with your perturbations, you now have perturbed images that are misclassified, and you can retrain your network that you got these perturbed images from using the perturbed images, but with the correct labels. So you can just add these to your training data, right?
Yeah, so now you are thinking ahead of yourself, which is great. Now you saw a problem and now you want to fix it. And we are gonna fix it in the next paper.
Is the next one just a GAN paper, basically?
No.
Okay, cool.
But for now, we are investigating the problem. We see that there is a problem, and the problem generalizes. It's not only for this particular network and this particular data set, it's actually universal.
When you say that the problem generalizes, does that mean that each network architecture with its own data set has a set of images which would get misclassified like we see here? Or do you mean that like this particular dog that you've figured out is misclassified would be misclassified generally by all of the networks?
Exactly. It's the second thing that you mentioned.
That's amazing.
You take this image, and that image is wrongly classified by this network, but then there is 11.7% chance that the same image is going to get confused. It's going to confuse another network, trained totally differently.
So if you build an adversarial example for one network, it's still roughly adversarial for many other networks as well.
Exactly. So this is an adversarial example for this image, but then that adversarial example is not only going to confuse this network, it's going to confuse multiple other networks.
That's fascinating.
Yeah, it's generalizing.
So it's not even like a special case of taking advantage of this one architecture. There's something about that image. Yeah, that's fascinating.
Yeah, it's amazing. And Parker is saying it makes sense though. All these networks have the same objectives and training data. No, that's the whole point. We are changing I think there is one part here that I'm not mentioning. I'm going to mention it in the next session. Even if you change your training data, you train your network on totally different training data sets, it's still going to get confused. There is a high chance that the same adversarial example is going to get confused by that network.
So you're saying that even if I take an adversarial image for a network that was trained on the non-perturbed image and show it to a network that didn't have that image in the training data, then that adversarial image may still get misclassified.
Exactly.
Okay, that's pretty wild.
That's wild. Yes, that's a serious problem.
Yes.
So, yeah, it's definitely intriguing. And there is another question from Brandon. Are there any papers that explain why certain data networks are more robust than others? What subfield would this be? So it's exactly the topic of our discussions in the class for I think 1 week or two. And then once I'm done, you should be on a good ground if you want to do research in this field. You're going to have enough background. And I'm going to tell you what other papers to read if you are interested.
So I'm thinking as a cynic now, looking at these misclassification errors, like it's always 100%. So 100% adversarial for the network it was designed to be adversarial for, and then it's 11% or 22% for the other networks.
Yes.
Is that any worse than just the background misclassification rate? And if it's making the same error rate as it would for any image, can we even say that that's an adversarial image?
No, these networks, most of them are making around less than 1% error.
Okay.
Or less than 2% error. And now
So
you're,
it is 10 times worse or 20 times worse. Okay.
and as you make them deeper, you are giving them more accuracy, more power. They're gonna make less mistakes.
It's a little bit more robust to these attacks. Yeah. Okay.
Yeah. It looks like that this autoencoder architecture is more robust, but still.
Something else I noticed that's interesting to me is that the adversarial image for the third line, the FC10-1, whatever that network means, seems to be the most adversarial across the board for all the other networks. So I'm curious about what properties you learn to exploit of that network, which are then like the most bad compared to the other networks.
I see. That's a great question. I need to see that. That's a great observation.
Like whatever blind spot FC10-1 has seems to be a very strong blind spot for all the rest.
And if you look, the average distortion is bigger. So the magnitude of this R is bigger.
Oh, so that could,
yeah, it's more noise. Maybe it's more noticeable to human eyes.
it could be, yeah, that it's most adversarial just because it is the biggest distortion.
Yes.
All right, thank you.
Yeah. Any other questions?